Okay, thank you very much for the invitation of the organizer. It's a pleasure to be here. And what I will try to talk in here is about the surface heat flow and why it's important for geodynamic purposes. Yeah. And let's see if I achieve that, yeah? No, I went backwards. Okay. This is the surface heat flow, the global database. It's from 2024, yeah, but I have to congratulate all the group that they did a great job, very necessary to put all together and all this data and compatibility between them and the errors and this kind of stuff. No, that was great. And looking this map, yeah, it already well, as was already mentioned before, there is many gaps, no, particularly in these areas. But anyway, you can already correlate. There's a kind of correlation between surface heat flow and the tectonics or global tectonics. No, we see these high surface heat flows in reef and this lower surface heat flow probably in more cratonic areas. Yeah, this correlation is not just seen at surface, you can also see at deep. Yeah? If you have, for example, here an example of a global BP model, yeah? Velocity model, you already see in the mantle, you already see that there is a correlation with the surface heat flow, higher surface heat flow in places where there is also related with this sometimes slow velocity, and well, we can say that there is a correlation. If we have a look now, a zoom in the Mediterranean area, we also find this in the western Mediterranean. Is an area with a tape at lithospheric at mantle levels. There is a low velocity zone, all this region here, no? That also is correlated with a higher general surface heat flow. And in the other side, we have here low surface heat flow also is correlating with these low velocity zones at depth. Moreover, if we have a look in terms of geothermal exploration, we see that according to this, the think geothermal energy, the top 10 geothermal countries where they are installed power generation are also in our areas. If we have a look, they mainly are in these areas, zones where you have high surface heat flow. There is also a kind of correlation, no? And even more, we can have a look, if we look here in the America, in the United States, there is this geothermal resource, high geothermal resource in the western part, where the surface heat flow are higher values. Meanwhile, in the eastern part, looks that is a lower surface heat flow. Then, what I mean all this? Well, this means that the surface heat flow has a clear correlation with what's happening in the lithosphere and in the mantle, and then will be is a good way to this, no? Has to be used, yeah, as a data. And what here I wanted to say, Why is important? What is the surface heat flow and why is it important? Well, this is probably obvious to all of you. What is the surface heat flow? Is the heat transfer from the air. Just to remind, is coming from the mantle, the heat that is coming from lower mantle, and after also the created the heat from radiogenic heat production in the crust. Yeah? How is calculated from the thermal gradient and the the gradient, that is the temperature, how it's changing in depth, and the thermal conductivity of the rocks. Yeah? Following this Fourier's law, yeah? And at surface we have that. Yeah? Well, this probably is obvious to all of you, yes. And also, as we were talking before, no, there's somebody comment that heat flow values can be affected, but a lot of external process like these ones, groundwater circulation, places where you have cold water going down, and then we will measure lower surface heat flow. Meanwhile, in places where the heat circulation, yeah, is going up, then the surface heat flow will affect to the temperature gradient, measuring higher values of surface heat flow. Then for geodynamics purposes, all these effects should be corrected, no? But anyway, as we have been talking before, isolating and adjusting all these contribution factors is quite complex and is highly site dependent. But okay, then what I will show here is how we have been using these last years, the surface heat flow, as another data and as another constraint for determining how characterizing the crust and the upper mantle. Yeah? Then surface heat flow by itself is not is very useful data, but needs to be integrated in a geophysical petrological model here. That in here, what we are using the elevation as a constraint for the model. Yeah, elevation, gravity data, geoid, the surface heat flow, and the seismic velocity. What is this model? This one is geophysical. We use all this data, and petrological in the sense that we are considering the composition of the mantle with the 5 main oxides and how it changes and the pressure and temperature. Then the density and the thermal conductivity and then the seismic velocities in the mantle are calculating according to this composition and pressure and temperature. And this is all integrated in this model that it will calculate the gravity and affect the gravity and geoid and the surface heat flow. Yeah. This data integration, I will show an examples here in the central Mediterranean. I will show probably just more in detail one of these profiles, the northern profiles, for timing reasons, yeah, well, we have been working in this southern profile in the southern Apennines, and then we are doing something in the Calabrian Arc, yeah. Well, just as was commented before, this high observe this high surface heat flow in the Tyrrhenian and in the western Apennines, yeah, that is all this magmatic area, and this low velocity, this low surface heat flow in the eastern Apennines and the Dinarides. Yeah. Okay, if we have a look this profile, this one here, yes, in the northern, crossing the northern Apennines and the Dinarides, this is the data. This is the data that we have to reproduce, to constrain. What we need that, this is the data that surface heat flow, the top, and then we have the geoid, the boogie anomaly, and the elevation. And then this is a model of the P. This is an example of one, velocities in the BP velocities in the mantle. That what they tell us is that there is a fast velocity zone that goes beneath the Apennines in the south-west direction, dipping to 400 kilometers depth, and to the other side, to the Dinarides, is dipping in to the northeast and is shallower. Yeah. Then taking into account this data, then collecting all the information that you can get at crustal levels, like geological cross-sections, geophysical data, that seismic profiles, reservoir functions, putting all together and changing the crust. We just change within the uncertainties. This is the crustal cross-section resulting from the model. Yeah? With this crustal cross-section, we find that we can reproduce this slightly higher surface heat flow in the Tyrrhenian area that will be due to this Tuscany magmatic province, with higher conductivity, probably heat production, and then we have these two dipping crustal crust below the Apennines and the Dinarides. Do we have a look to the lithospheric scale? There is this thinner lithospheric mantle beneath the Tuscany province, that it will give a higher thermal gradient and a higher, then results with a higher surface heat flow, yes? And also in this, I will not go in detail, but we try the model with these deep slabs, with this deep lithospheric mantle and without, and we saw that in order to adjust geoid and gravity and elevation, we need these lower temperatures bodies that in turn results in a low land denser. They are colder, then they are denser, and also they agree with these two fast velocity zones that are beneath the Apennines and beneath the Dinarides. Yeah. Then putting together all this data, elevation, gravity, geoid, topography, and seismic velocity, we finish with this model in the northern Apennines that is, we interpret this geometry and as a bidirectional post-collisional delamination of Adria mantle. What we understand about this delamination is delamination in this definition, like a subducting plate delamination. What it means, that was subducting. Then at some point, the oceanic part, and then at some point is the collision with where the continental lithosphere tries to subduct, is more buoyant, and then there is this upper mantle going, sublithospheric mantle going up and peeling the lithosphere mantle of the Adria plate. Then the crust remains on top. Then the Adria crust goes from the Sava Sutur to the Corsica. It's the same crust, the same characteristics, and the lithospheric mantle is delaminated in both sides. We see that with these two continental slabs with the two mantle wedges in both sides that gives this hot zones in the Tuscany magmatic province with this magmatic area and all this surface heat flow as well higher, and this also these lengths of these slabs. This is something also interesting. These lengths of this slab are are in agreement with this subduction delamination of the mantle lithospheric mantle. Yeah. Then we did the same in the southern. We did a profile of the southern part. Yeah, the southern part that is in the Adriatic, also high surface heat flow. The difference in the southern part is that there is this slab or this low fast velocity is not attached to the surface. Then this has been modeled as we find here that there is there is a gap, there is a detachment. There's a kind of slab tearing that could be due to previous transform faults, maybe. And also there is this magmatic area in this area with mantle exhumation, with serpentinized mantle exhumation that is also compatible with the high surface heat flow in this area, yeah, and the formation of these basins. In the Calabrian, the difference with Calabrian is that there is this continuous slab, and this is a working process. I will not show now, but also this high surface, a bit scattered, but high surface in general as average, and lower in the Ionian part. Yeah. And well, I will go this just say that as combining all this data, yeah, putting together, integrating this geophysical and petrological data, we could describe the geometry of the Adria plate, and in this area, how and also at a crustal scale, and also at mantle scale, we define these two geometry, these two bidirectional delamination, and this. And then I just want to show as to finish that, yes, this is just to show as a present day reconstruction, yeah. And then we did some, this how it could happen, this delamination. I will not show the model itself here, all the model, but using aspect, we could see how a process of delamination is affecting to the surface heat flow. That is what I will just show in this model. No, we have this delamination model there. What's happened? This delamination, we have sublithospheric mantle going up, the lithosphere gets thin and getting thin, and is transmitting. We get this is the surface heat flow. That is will be the start, and with the time is getting wider because it gets a wider zone that is here where you have this melting also, no? Because we have high temperatures in this area. And then this, we can see how the surface surface heat flow is getting this maximum wider and is moving with mantle delamination. This second peak of could be related also with the, in here you have this, due to the delamination, the crust is getting soaked down, is getting thicker, and more radiogenic heat production. Well, other process of delaminations, other process here in retreat, how you could also correlate the processes with the surface heat flow, that I will not go. as a summary, this, no? How important is the surface heat flow also is very necessary. I appreciate a lot the work done during all these years, and we will keep using it for integration in the geodynamic modeling. Thank you very much.